Oh, well, we have quite a group here now, so let's go ahead and get started. I'm Elaine Boyd. I'm the Executive Director for the New England Section AWWA, and we also have Ramona Longo with us today, too. She's the Connecticut Section Executive Director, so welcome, Ramona. Thank you for joining in on our webinar, and I'm going to turn the time over to one of our board members, Ryan Shea. Ryan's with the Boston Water and Sewer Commission, and I appreciate him for moderating today's session. So take it away, Ryan.
Sure. My name's Ryan Shea. I'm the Acting Director of Construction for the Boston Water and Sewer Commission and YP Chair on the New England section. Very happy to be here today, and I'm curious to see how many folks do we have from the New England section. We could get a hand raise. Chiho.
Yeah.
Mr. Fleming, Ms. Velasquez.
Aaron.
Nice.
Nate.
So we
yeah, great.
Chris. Nice. And then how many folks from the Connecticut section? If you don't mind raising your hands. Nice. Pretty good split here.
Mm-hmm.
And then do we have any guests just tuning in? Anyone? On New England, on Connecticut? Friends from afar? All right. Good to know. Steve, our presenter, is just telling us he's down in South Carolina. So with that said, I'm going to get started with a couple of shout outs for the New England section. So don't miss our next upcoming webinar. It's on the lead and copper rule revisions and improvements. It's going to be on October 10th, 2024 from 1 to 2. Just like this session, TCHs will be awarded, and we're going to mainly talk about where systems are most likely headed to have action levels in exceedance of the lead and copper rule initiatives and what water systems should focus on in 2025 and beyond to meet compliance. Our speakers are going to be Carly Sampson. She's a water process engineer from Corona Environmental, and she's an adjunct professor at University of Rhode Island. She is also on our New England board, as well as Miss Sandy Kutzing. She's Senior Vice President at CDM Smith. If you guys like this one, definitely tune into the next one coming up. So in addition, we're also in the New England section planning a couple of events. Our next big one that we're really looking forward to is at the IDEX facility. It's another event that's going to be in October. It's going to be Thursday, October 24th. We're going to have a meetup, get together for a social, have some pizza and a couple of drinks. And then on Friday, October 25th, there's going to be a training tour and lunch at the IDEX facilities. I think if I missed anything else here, but yeah, just come. It should be a lot of fun, and we're excited to have some events at the IDEX facility up in Maine. And then as part of this facility tour, you're going to have a unique opportunity to explore IDEX. They're a leader in total water solutions, testing products, services, and support. You'll get an inside look at their facility, which is going to be really interesting, and you get a chance to firsthand see where some groundbreaking, really innovative water testing products are research developed and manufactured. There will be live demonstrations, and like I said, you'll be able to see how they make their products and how they make some of their rapid, accurate tests and their ranges for design parameters. Cavanaugh, he is president and CEO of Cavanaugh and Associates. He's a creative visionary with unshakable dedication to the environmental stewardship and preservation, which had led him to work with public and private sectors, both nationally and internationally, for over 3 decades in developing innovative solutions to some of today's most challenging issues. Steve has dedicated his career to advancing water efficiency practices and harnessing renewable energy. His next frontier is illuminating the carbon associated with utility leakage and helping chart a course for effective reduction. He serves as the chair of the International Water Association Water Loss Specialist Group, Leakage Immersions Initiative. Steve has a BS in Civil from NC State University, and Steve is a licensed professional engineer. I can also add a personal note that during my MS thesis work at Northeastern University, I was working on a water loss project. I met Steve at a ACE conference, and he's been a mentor and friend for many years now and helped me through my thesis. He's an awesome guy, and I'm really looking forward to learning about not only water loss, but also what we can talk about in terms of carbon reduction with that work and really compound those efforts moving forward. So with that said, I'd like to turn the presentation over to Steve. There will be TCHs awarded at the end of this webinar. A recording and a copy of the slides are available on the New England Section website. And I believe the folks in Connecticut, if you want your TCHs, you're gonna have to hang around for a brief quiz. Beyond that, we'll turn it over to Steve.
All right. Thank you, Ryan. Thank you, Elaine. If all those, if you can, go ahead and mute your mics. I'm getting a little bit of feedback. Give everybody just a second. Oh, that sounds much better. All right. So it is good to be with everybody today. I'm excited to talk about leakage emissions and kind of this new frontier from a funding standpoint, and to be back at the New England section, sort of doing some education. So and Ryan, I appreciate you talking about the Water Loss Control Committee and the great work that the committee has been doing, and certainly your involvement. We certainly benefited from your time, active time there for sure. So again, sort of this carbon leakage carbon nexus, some exciting stuff to talk about today. And I think we probably have 20 or so on the line. So I do want to have it interactive, as in I'm going to ask some questions in a bit. Kind of hopefully have everyone sort of maybe chat in some answers. Also going to do some hand raises, so be ready for that. Let me sort of help set the stage. And I would say that I'm super excited that, of course, I've been in non-revenue water, as Ryan said, for probably close now, going on 25 or so years, talking about water loss control, leakage management, non-revenue water programs. And I'm now excited of this direct link between leakage emissions and actual leakage and distribution systems. So setting the stage a little bit, S&P, a lot of you that are on the line from utilities have bond ratings. You have funding associated with that bond rating. We're now seeing S&P start to really lean in on distribution systems and sort of how they are interacting, and they're starting to publish some national and international figures. You've by chance you for sure read ahead 126 billion gallons. What does that mean in U.S. familiar units? That's 321 or so billion gallons that are being lost every year in terms of leakage. There's some statistics there, what that means relative to countries and so forth, the revenue. And then this third one in purple is really starting to make the tie between that leakage and the billions of kilograms of CO2 or carbon dioxide. And so that is an interesting statistic when we start to put these together and think about them. Now more on the utilities themselves, kind of the sustainability, looking at non-revenue water, again, from S&P. It's deterring investment in water infrastructure. And then also the importance of mitigating greenhouse gases. And this is thinking about water utilities that are actually starting to have either their customers or as part of their policies and their thinking of, hey, what is our carbon footprint? So my first question to you is, if in your utility you have started or had someone ask the question about, hey, what is our carbon footprint, or you are calculating your carbon footprint, I would love for you to do a quick hand raise if you could. And again, that's just at the top, just to do a quick hand. Excellent. So a couple, 2, 3 that are. So that's outstanding. So you already are in this gear, and that's likely why you're interested in being here. Thank you. So to sort of put this on the stage, I was at the Water Loss Conference, the International Water Association. I'm a member of the Water Loss Specialist Group in Prague in 2022, and we were sitting around really commenting on how there's really been a lag, if you will, in attention on leakage management and funding globally of leakage reduction projects. What we did notice and talk about was there's been a significant amount of funding as it relates to greenhouse gas reduction. And so literally as a function of this conference, and you know how groupthink and you've got a number of the world leaders that are together, we basically said there is a definitive link, but we need to show that definitive link between distribution system leakage, and I'm going to do a lot of explaining what that means in just a moment, and carbon. And if we can show that direct link, and we can now say, hey, if for a carbon reduction or a greenhouse gas reduction effort, if we can direct some of that funding to leakage reduction, then kind of the self-serving goal of reducing leakage in distribution systems, we can open up that flood of money that Elaine was talking about because of all of the carbon money that is out there. So our initial goal was to update the water balance. I'm going to describe that in a moment, and then really create the carbon water balance that we could definitively be able to push out globally. So we built the IWA leakage emissions website, and this is live. It is leigroup.org. I really encourage you to take a look at this. It's very, very active. And we started meeting technical professionals, 55 professionals from 22 nations originally came together. It's now almost 100. I think it was 96 that are now a part of this group, representing about 36 nations now. But we worked together for probably about 3 or 4 months in kind of deliberations and meetings of really looking at this linkage, and put together the basis and the technical memo and published the white paper. And the white paper describes this very definitive link between leakage, distribution system leakage, and carbon. So if you look at, and I will actually through the Q&A, I'll drop some of these links in. They're on the LEI website, but I do encourage you to go out and read the white paper and take a look at it. I'm going to go into great detail about that now, but this sort of gives even more of the historical footnotes and the science behind what I'm going to share. But it is there, it's published, peer reviewed, and as I said, now it's grown to over 30 nations that are quote signed on. The Water Loss Control Committee of American Water Works Association unanimously approved the committee report that is this information that I'm sharing. It has been North Americanized, if you will, just a bit, that is in our familiar units and so forth, but it's exactly the same methodology. It is making its way through it's made it through the division. It's now headed to TEC, where we expect full publication in the journal in early January. So pay attention to this slide. You may see this later in the form of a technical question, but this is the basics behind the calculation, and that is to calculate the carbon associated with distribution system leakage and the carbon intensity of the water utility itself. We really need 3 things. We need to know how dirty our energy source is that's coming into our distribution. So everyone buys your power, imports that power from some electric wholesaler. There's so many kilowatt hours every year that you bring in. Well, we need to know a little bit about what I call the dirtiness of that power. The great thing is, and I'll show some resources in just a moment, but every electric utility provider now has a rating of the grams of CO2 per kilowatt hour. and it's based on their fuel mix. So it could be that it's natural gas, it could be that it's coal, it could be that it's wind, solar, etc. But there's so many grams of CO2 for every kilowatt hour. The second thing we need to know is how much energy does the utility use on an annual basis to transport, treat that water that they put into their distribution system on an annual basis. And this is in the form of kilowatt hours per million gallons that we are able to relate this to. And then obviously, how much water we produce every year. So that gets us the pieces. So then it's math. It gets to a utility-specific carbon intensity, and this is in terms of grams of CO2 per million gallons. So if you've got grams of CO2 per kilowatt hours, you know how many kilowatt hours you use on an annual basis. You know how much water you produce on an annual basis. We can easily get to our carbon intensity for the water utility. So important pieces there. It's the energy source and how dirty that is, how much water we produce, and how much energy it takes to produce that. So just in your mind to grasp this a little bit, if we are a Caribbean island and we are tankering in our fuel source, then we're driving a turbine to actually create the electricity, and then we happen to have a desal plant. Intuitively, everybody probably gets it pretty quick that that is probably the dirtiest energy source, what we're having to tanker in, produce the energy, and then the most energy that we would need with a desal plant. Conversely, if we are Vienna, Austria, and our water is coming from the mountains, very, very little filtration and very, very little pumping, and they have a lot of renewable resources, then their utility specific carbon intensity is going to be quite a bit less. So this is how globally we've got a uniform way that we can calculate and measure this. And it's very, very straightforward. So our data, where we get our data from, this is a resource. This is electricitymaps.com. And all of these resources are on that LEI group website when you take a peek at that. But you can mouse around this map. I've sort of centered in on Indiana, I think, here in this particular area. So the Mid-Continent Independent Transmission, their carbon intensity is 555 grams per kilowatt hour. And so kind of reading that down at the bottom here of the table. So this is a way that you can quickly pick off, and then even more granular, each individual utility provider has this information available to them, electric utility provider. And please, as I go, if there are questions for understanding, give us a hand raise, give me a hand raise, and we'll take a look at it. So I want to spend just a few moments, and I'll do a question back to you. This is the AWWA, and it was brought and adjoined from what was originally developed from the IWA, the International Water Association. But this is the water balance. This is the basis for all water distribution systems, of which they manage use and loss in the top-down water balance process. It also really underscores the fact that there is no unaccounted for water. And in fact, this is an important piece. I encourage you to write this down. AWWA, and I realize I'm bringing breaking news to you, but in 2003, AWWA abandoned the use of percent unaccounted for water to describe utility system efficiency, operation, and a performance measure. Let me say it again. In 2003, AWWA abandoned the use of percent unaccounted for water. Unfortunately, many of the states still have outdated policies and practices and reporting that still have that language in there. We have a very vibrant outreach and education subcommittee of the Water Loss Control Committee that continues to educate and is making great strides to help utilities move to the best practice that I have on the screen here, which is really starting to look at our water by its categories, its components. So if this is the first time you have seen the AWWA water balance, please do raise your hand. I ask this question almost every time I speak. I'd just like to know if this is the first time that folks have seen it. Great. Couple, that's good. So thank you for being on here, and I'm now going to sort of explain how this works and why there is no unaccounted for water. It is a balance, and each of these columns equal. So if we look at it, we have our first component is how much water we're putting into the distribution system. And this is an important piece, that some of this may be coming from our own sources, and some of you may be importing all of your water. You may be getting it from a wholesaler. So you're either making your water, producing it, and delivering it in a distribution, or importing your water. The addition of those two gets us to our total system input volume. Now, the same way we're importing some, we may have emergency connections, or we may be a pass-through system. So we may have water that we are exporting out of our system. So it's important that, and from the very beginning, we take that total system input volume, and then off the top, because it's not within our system boundary, unless the takeoff is at where it has gone through the system. Let's just call it the exit end of our distribution system. But where we're drawing the boundary, now we get to the total water that is supplied into distribution. So that's our water supplied. And then again, a balance. All of these columns are now equaling. So of water supplied, it's either authorized consumption or it's water loss. And in many cases, this is where utilities that are trying to take a look at and learning these best practices sort of stop. They take this one number of water loss and they divide that back through by, many cases, it's the total system input volume, and that becomes their percent unaccounted for water. And in many cases, their strategy is they start to attack this as leakage, or they say, well, it's all a metering problem, or they're just not sure. But it's really not telling us a lot about the strategy that we should be taking on to reduce our losses. So we have to go further, and we have to break down that water supplied as either authorized consumption or loss. But we break down the authorized consumption as either billed authorized consumption or unbilled. And it's okay if it's authorized consumption for us to have unbilled authorized consumption. I'll talk about that in a moment. This is our largest number, most always. This is our metered connections, and it could be that it's unmetered, but also billed. But our metered connections are our largest component. These are our standard meters that are out there that we're billing our customers monthly, quarterly, etc. That also is giving us what's called our revenue water. So this is the water that we put into the distribution system within our system boundary, and it's water that we get a return. So we get revenue on that water. Now, the unbilled authorized consumption, maybe to do a couple of examples of that. So in this, if you look at unbilled but metered consumption, this could be that it's the public service building or the utility water department or the wastewater plant, where it may have a meter for tracking, but we don't send a bill. And that's okay. That's a great thing, because we are accounting for that water, and we help to put in place better ways that we are measuring and managing that water. The other side of this is the unbilled unmetered consumption. And these are things that when you start really tracking it and building your team and having the conversation about it, you can really uncover a lot of these that are going on in the system. It could be that it's flushing. It could be that it's fire department usage. It could be that it is testing out there in the distribution system. A number of things that are authorized, unmetered, and unbilled, but they still are in the authorized consumption category. So it's important that utilities start to get their hands around and track this on a monthly basis. There's a saying that what gets measured gets managed. And so if you're now starting to have to report that, just making notes of it. Hey, when you're out there flushing, let's get a start time and an end time, and then let's understand what flow rate we were flushing at, and then tabulate that and look at it and track it on a monthly basis. If you're trying to do this at the end of the year, it's not enough granularity, and many times it's grossly missing the estimates, if you will. So now we'll swing into the water losses category, and I want to take the time to really break these down, and that it is either, our water loss is either apparent loss, also known as commercial losses, sometimes called paper losses. And the brief definition of this is it's the water that gets to a customer, but it's not properly measured or billed. So it got to a customer, but for some reason it wasn't properly measured or billed. The largest component of this always is in customer metering inaccuracy. And this is the nature of meters. It's getting better based on the solid state meter technology that's coming in. But the majority of meters in North America are mechanical style meters, nutating disc. And so that meter is actually not going to get faster over time. It's going to actually slow down based on what's in the tuberculation that's in the water and the wear and tear on that moving part. So customer metering inaccuracies is a big portion of this. Systematic data handling errors between the billing system of the date and time and measurement quantity of the read to the point at which the bill goes out the door, and then the corrections, the errors, the stopped meters, all of those things that happen in those handling aspects. And the other, we from a friendly way, call it unauthorized consumption. I call it more directly theft, people helping themselves, and that is a challenge in distribution systems, some more so than others. But the sum of these three really get us to what is the apparent loss or the commercial losses. It's important because that's different than leakage. And this is where we're going to really focus our time on in the carbon discussion here in just a moment. But it's important that this water balance and the methodology and these best practices that we really latch onto these as well, because if you look at this without doing an appropriate review and evaluation of your apparent losses, it's a balance, and the resultant is system input volume, breaking out how much is actually water supplied and distribution, minus our authorized consumption, minus our informed estimates, and through testing of customer meters, our apparent losses, equals on a top-down basis the real loss. And so this is our resultant number that now we can look at and really start to take actionable steps on. So apparent losses are valued at what we could sell the water for. Conversely, real losses or leakage in our distribution is valued at that next marginal production cost of the water, that next unit of water. So two very different cost and value components, and we really are pushing utilities to start looking at their non-revenue water in terms of the volume, the value, and also how valid the validity or the reliability of that information. So any questions on sort of the water balance? This is a foundation because I'm about to show you the carbon water balance. Any questions or interactions here before I move forward? All right. So I just showed you the water balance, the top-down methodology, but in leakage management, you have to now break the leakage down, because if you remember on that previous slide, it said not broken down, how much was on transmission mains, the overflows at storage, and service connections. Where we start to break down leakage is we get into what's called a leakage component analysis. And this is important to show how we go from the top-down water balance into a component analysis to say, okay, utilities are now, at least through several research papers and best practices and technical presentations, they're now starting to track how much what they are responding to, what we call reported leakage, the leaks that find you. They come to the intersection, they close the streets, they flood the Los Angeles Lakers floor. I mean, it's the ones that come to the surface. You have to interact with them. The other side of this, and so now we're tracking it. We're saying how many leaks did we respond to on mains and service lines, and then making reasonable estimates of that total leakage based on runtime. The other side of this is background leakage. This component here, very important. These are the weeps and seeps that are a function of the physics of your system. Every distribution system is operated under pressure by law from a safety and water quality standpoint. So there are so many miles of main, that the operating pressure and the number of service connections. Those are the elements plus your infrastructure condition factor that make up what is your technical minimum. Unless you replace the asset, the pipes, or unless you modulate or change pressure, you're going to have that amount of background leakage. So this center component, this unreported leakage, that is the leakage that we can interact with. And so way back in the beginning, when I was talking about how to tie carbon money to try to drive leakage management, this is the piece that we're really focusing in on. If we now are looking at finding funding to help drive our unreported leakage or our hidden loss, our hidden leakage component out here, we may can get somewhere. So in this case, we have the example. So 6 billion gallons of water, water loss is in real loss from our top-down water balance. We have 500 million gallons that's reported leakage, background leakage at 2,200. The recoverable component of this, 3,700 million gallons or 3.7 billion gallons. So now I want to go back in your mind and think about those three things I talked about to get us to what is the specific carbon intensity. So it's the energy source in terms of how dirty the power is, the grams of CO2 per kilowatt hour. It's how many millions of gallons we put into the distribution system. So total system input volume here, let's use for water supply to follow that same example that I was doing before. So that's 45 billion gallons that's going into distribution. And then we also know, how much energy in total kilowatt hours that we use to produce that water into distribution. So we now can calculate that carbon intensity and then apply it to every component in our water balance. So that is how we get to the total bogey, if you will, of real loss. So following through on that same example, this is metric tons of CO2 per year. So in this example, based on the carbon intensity, it was pretty close to 1. You can see that we had 3.7 billion gallons equaled 3,780 metric tons of CO2. It's not always like that. It just happens to be in this example. So now when we're positioning this project and moving it forward, if for those of you who said, hey, how much, what is our carbon intensity, and starting to look at our carbon footprint, now you're able to say, if we interact and go and remove 3.7 billion gallons of leakage from our distribution system, we're able to remove 3,780 metric tons of carbon. And just kind of a quick note, 1,000 metric tons is about 217 cars off the road per year. So a lot of utilities start to equate that to something that people can latch hold. So in this case, that's 850, 820, something like that, cars off the road. Continuing on, this is a little bit of the math behind this, and I mentioned the committee report from AWWA that's now approved, but another example, so this is 10 billion gallons per year, reference carbon intensity again from eGrid or electricitymaps.com in terms of grams per kilowatt hour. What is the total energy usage for the water utility? That gets us to a specific utility carbon intensity in grams per million gallons. And now we have a target leakage reduction that we have in this. So this is 1.4 billion gallons, and then our carbon reduction and what that means of total metric tons per year. So again, just something to sort of latch on relative to how you would go about calculating it. There is a carbon calculator, a leakage carbon calculator on the LEI website as well. So this flood of money, and Elaine brought that title into play, and I was like, let's call it a spigot right now. We hope that it will turn into a flood of money, but we are working hard on what's called carbon leakage credits. And so we got the concept from what's been happening in the agricultural side, where you have the methane avoidance from swine, dairy, poultry farms, and you're actually able to create a carbon credit as you're able to capture that. Well, it would be that if you really fast forward this, wouldn't it be interesting to where you now have outside investors, let's say a BP, Shell, Nestle, that may have a carbon intensity for their operations of what they do of 125. So for them to get to carbon neutrality, what they have to do is invest in projects, opportunities that have a negative carbon intensity. So, the dream scenario that I see out there potentially is let's just say somebody is now coming to Mass Waterworks or Hartford and saying, hey, I want to buy the rights to your leakage. And you have gone through the math, you've shown a project, and it shows that it's going to reduce 2,000 metric tons of carbon. There could be a negotiated payment for that carbon in terms of the carbon leakage credit that the utility can then be able to use and leverage to perform the leakage reduction project. This is where we're headed. We're trying to advance that concept of the carbon leakage credit. So that may be there in the future. We still are working through rating agencies, Gold Standard, Vera, CAR, those out there that we can get the methodology to where it is something that is approved. Quite honestly, there was a lot of fraud and a lot of greenwashing that was going on early, and so all of these registries have pretty much said we're stopping. We're not issuing any new initiatives or verification steps or processes. But we have it now. We have the International Water Association first, and now it's joined by the American Waterworks Association, or almost through all of the channels of the AWWA, to get us what we need, that we've got a verifiable methodology to be able to calculate that carbon. So another thing that, and this could be why some of you that raised your hand have said, hey, I'm interested in this, is the states are starting to lean in and have their own targets. And so basically, I'm going to briefly talk about what, on a global sense, what's called NDCs, or nationally determined contributions. And every country that signed on to the Paris Accords, they have things like, we're going to reduce to 1995 levels by 2030. So they have these goals. What we're doing is we're now going back to those same ministries of the environment that have these targets and goals, and we're saying, look, if you fund a leakage reduction project and we're able to reduce this many metric tons, you should be able to claim that. This is helping you get towards your targets. Well, in the States, we have something that's very similar. So I've got New York highlighted here, but obviously there are several in folks that are on this call of where there's statutory targets, or it may be that it's executive targets. But in this case, it says, you know, they set them in 2019. They're going to get 40% below 1990 levels by 2030. So now if we can go to the states and say, look, fund leakage reduction projects, this helps you get to this goal, this could be another driver. And again, that's what the original initiative was. It's how can we tap into these funding sources to better drive and fund leakage reduction projects, and obviously reduce greenhouse gases along the way. It's really kind of a carbon insetting methodology. And so just a slide there. And then, you know, kind of that last bullet, every ton of carbon avoided by leakage emissions based programs can help U.S. state and federal governments inset against their total emission goal. Just a couple more, and then I'll get to a little bit of a Q&A. So a little bit of the horizon piece. I mentioned the verification bodies working on that gold standard Vera CAR. We have on the far right of the leakage emissions initiative, we have a case studies tab that we're now filling up. Our mission is show as many water utilities of what they've already done in terms of leakage reduction, get those out there, and then be able to point to them to other utilities to see that say, we have reduced this many millions of gallons of leakage. And oh, by the way, that calculated out to this many metric tons of carbon. And so the more we can have those case studies, you know, we have New Jersey American has a case study out there. We have Jamaica has 2 out there. We have one in Italy. We have one in Sub-Saharan Africa. So, and we've got MODOC in California that's working on pulling them. We're trying to get as many case studies to show what we've already done to be able to help funders to see the value of funding these projects and the viability of it from a carbon standpoint. So we're trying to educate global financial institutions. And then some of the things that I hear, I spoke at a Sustainable Water Management Conference, I guess it was last year. There's a little bit of a pushback. It's like, why should we be rewarding water utilities when they should have gotten this leakage out anyway? And it just was, I understand that, but I also know Ryan mentioned before I started speaking about lead and copper and, PFAS and everything else that utilities are having to deal with. If it is not, stopping the utility from operations, unfortunately, leakage reduction kind of gets pushed back. In some cases, when it's drought or where supply constrained, then it does move to the forefront. But this sort of leaking, lagging mindset or misconception is really what I pushed back and said. But if this advances and puts priority back towards leakage because the funding is there to do it, then why would we stop it? It makes no sense to do that. And that did get a little bit of traction. Also, the time horizon to count. So if you think about it for just a moment, if you did not interact with that leakage, leakage has a natural phenomenon that occurs, which is the rate of rise. If you don't interact with that leakage, then it is operating under pressure. Those leaks are getting larger over time. So there is a natural rate of rise of leakage. So if you think about it, we interact, we repair that leakage, we've stopped that, and we've also stopped the rate of rise. So that's why year over year, we're saying that we're avoiding the carbon that would have gone as a result of the energy that it took to produce that water with that specific utility carbon intensity. So anyway, we're working on that horizon. Let me pause there and maybe get folks to come cameras on or raise hands, but let's have a little back and forth. Ryan, is that what our next step is, or was there some interaction that we needed sort of business wise before we go to that?
All set, ready for Q&A.
All right. All right. Let's hear them.
Steve, I have a question. This is Elaine.
Sure.
First of all, I want to, for those of you in utilities that have not gone through the water loss balance, I would highly suggest it, because it's one thing to identify all those areas of where your water's going, but there are some real life case studies that I've even been involved in where there's been some significant revenue, like I said, brought into the utilities through that. In fact, I'm just going to mention one that I was involved with, where water utility was not, their meter to a commercial user was off by 90%.
Yep.
They were not billing a user $1 million a year. So they were able to recover that. And maybe, Steve, you want to talk about some other kind of not so, some other big type of things that could be redeemed by doing that water loss balance.
Yeah, that's a very good point. Let me go back to that slide and I'll share the balance. So in many cases, and what Elaine just spoke about was, I didn't spend a lot of time, but if you see that little parenthetical here, it says corrected for known errors, corrected for known errors. And also on the water exported. So the 90% that Elaine was talking about, this is a systemic problem across North American utilities, and that is that we have water that's going into our distribution systems, or that we're exporting and selling, or that we're importing from. And that meter may be calibrated, which gets amalgamated into we have our meters tested. But in reality, the calibration is basically the signal. It's taking whatever it was measuring, if it's rotations, pulses, pressure drop, and it's converting that through a signal into millions of gallons or whatever the recording piece is. So, and that typically happens, through a 4 to 20 milliamp signal process. And so the calibration says, okay, 4 milliamps equals zero flow, and 20 milliamps equals max flow or full flow or target flow, whatever it might be set up for. So the utilities, as they are testing their meter, are doing that signal calibration and finding that many times that's accurate. It was just a skosh off, and so they tweak it. But what's not happening is a flow meter verification, where we are actually doing a secondary test. We're flowing the water through that meter in a comparative analysis. It could be at a water plant using a clear well and taking a known quantity of water through and measuring it. That's a flow verification test. When that is done, and that's why in the water balance, it specifically states there can be very, very significant errors. And in many cases, your starting number is grossly off. And then the great example Elaine has is it basically, it was misbilling on the water exported. Large customer meters, the same thing, the exact same thing. They may be sized for the factory that was there, and now it's a upholstery company that's using a big warehouse space that was something that used a lot of water, and it doesn't now. And so that meter is, I mean, it's never going to measure properly. So there's a lot of revenue to be gained. One quick side note, because Elaine, you bring it up, and that is the optimization of the large meter testing program. I'll give you a $1 million solution today. If you will go back in your water utilities and you will sort your meters by revenue, by month. So your largest revenue, top to bottom, and you start looking at those meters, you'll probably find in most cases that it's an 80-20, that 80% of your revenue is coming from those 20%. Well, when you look into those at the cost of the test, repair, and retest versus the revenue that's coming, you may get some significant bang for your buck instead of doing what a lot of utilities do, and that is our large meters, we test every meter annually. Well, some of those, you're never going to, it's never going to pay for itself because it's just not producing that much revenue. So go back and readjust your large meter testing program and sort it by revenue from top to bottom. And that's $1 million idea today of this webcast. So it was worth the price, whatever it was, Elaine, right there in that thing, not to mention the carbon. So anyway,
we paid their salaries for quite a few years there.
There you go. So the other step of this is as many times as I have spoken on this, and that we feel like everybody has seen the water balance. Just in this sampling of 14 or so that were on, there were 2 that had never seen it. And I would also hazard that probably the majority of the utilities are not auditing, that are on this call, are not auditing every year and then and taking action from those audits, which is something that, again, as you start to do it, you really can capture some significant revenue, and you're also going to change the dynamic of your conversation. Carolyn, go ahead. I see a question.
Hello. Yeah, taking action from the audit is a key. But my question is about the categorization of the leakage, the reported, unreported, and background.
Yes.
Are those the reported leakage is an actual number from
That's right.
Right.
That's from you. Mm-hmm.
The breaks that you fixed and you estimated the rate. And then the unreported and background leakage, is that like a published ratio that's available somewhere?
So the background leakage, let me go to that, because the unreported is the deduction between the two. And what you may have discovered through proactive leak detection. Let's just say you've got a crews that are going out there and they're sounding hydrants and valves and so forth. Then they are on a year building that component. This is called a component analysis of breaking it down by its components. So reported leakage, that's coming from you, what you're doing and you're responding to. It's what gets reported to you. But the unreported or hidden, then if you've had crews that are doing that within your audit year where we're doing this component analysis, then that's part of it. But usually it's the remainder, as I was showing in the math here. You're taking this background leakage. It is basically the 3 factors I described: your miles of main in your distribution system, the number of service connections that you have, because those are actual taps. Those are weak points in the pipe where the pipe has been interrupted, if you will. And then the system operating pressure. And there is a formula for that. It also includes the infrastructure condition factor. So it is things like age and also the material type. But the main elements are miles of mains, system operating pressure, and number of service connections. So if you look at the free water audit software that is available from AWWA and you click on the definitions tab, you'll see the exact formula in there for what's called the UARL, unavoidable annual real loss.
Okay, so it's in there.
So
It's in the software. Great.
That's right. It's a great question. And the fact that you're asking about how to break it down, I would say 3% of the 52,000 US utilities are not even looking at this proactively of how to drive their leakage reduction project. But this is how it's done. Great question.
Thank you.
So what about the carbon? Is that too complicated for folks to sort of grasp, or is it something that makes sense? Let me go back to that definitions tab. Really the components of it, how dirty is the energy? And hopefully by me giving the example of the Caribbean island and tankering in the fuel and how dirty that power was, and then how much, if it was a desal, that uses quite a bit less than certainly the Austrian system that I described in Vienna. And then obviously how much water you're producing. Does the logic make sense? You take how dirty it was coming into us, how much energy we used, and how much you produced. Okay.
Yeah, Steve, could you go back to that map that showed that? I thought that was quite interesting. So it appears that the New England area is kind of moderate.
Yeah,
I'm
gonna go live. I'm gonna go live to the LEI website. Get out of that, and I can do this very quickly. Group, and let me show you the actual. We'll go right in on New England as an example. So resources. Let me get the share going again. So I'm on the LEI website now, and I'm going to resources. Here's where the white paper is. So if you look in the resources, the very first tab you'll see is the actual white paper itself. A version of what I just shared is there of this presentation. There also is a leakage emissions calculator. So the calculator that I showed the math is right there. It's an Excel spreadsheet. So I encourage you to go in and you can calculate your own carbon intensity and get there. Also, the case studies I was describing, there's a template. If you have done a leakage reduction project, there's a very simple template of how you can get that posted. And then we've got 4 or so case studies that are there. We need more and build them. I mentioned the 90 or so that are involved and active in this. You can mouse around and see, but these are all of the countries that are involved and very active in the leakage emissions initiative. But let me get to the calculator for come on. There we go. Electricitymaps.com is the resource. And we'll go right in to Connecticut. And it's showing 333 grams of CO2 per kilowatt hour. And this is updated all the time relative to the data that's there in the electric utilities. Also, we'll make a comment, and that is, I've had some people say, well, gosh, we're Holland and all of our power is wind and all of this. And the reality of it is, if you're using renewable energy to, drive leakage to help you on leakage of a waste, I mean, you're taking that renewable energy away from something else. So, I don't always say there's because you would reduce all leakage if you could. We can't, and that's what we talk about, the unavoidable. But I would also say you can utilize wherever you are on the carbon intensity that's coming into the utility itself, and just use it from a calculation standpoint to be able to help drive the reason to do the leakage reduction project. But this is that resource, Elaine, and you can
Okay.
mouse around and see. So
That's great.
And it's
what's
global.
What's the website? Is it LEI?
Yeah, the website is leigroup.org. leigroup.org. And I'm going to drop that in the chat.
Yeah,
Oh, thank you. Thank you, Elaine. Perfect. And then you can go to resources and be able to pick up on any of these resources. So,
yeah.
all right.
Perfect.
Any other questions or comments? Great,
Carolyn?
Sure. I mean, how realistic, or what is a realistic timeline, do you think, before verified renewable energy certificates or, carbon credits would be available for this activity?
We think, well, first of all, right now, insetting is very real. So, but the utility monetizing and get paid, we're concerned on one hand of the carbon leakage credit that it is so undervalued. So, as an example, planting trees in Brazil may get you $5 per metric ton. I mean, we don't want it to be something that there's this big, well, let's do all of this to get these verified, and then it's at that level. That's really no money. So, even if you monetized it for 10 years. So, but if you're taking it and all of a sudden now it's $200 per metric ton, then we're talking, and that's monetized for 10 years, and that's something. So we're trying to find the right balance. And we believe that carbon insetting and showing Department of Energy, US EPA, State Revolving Fund, that this is, now you've got the utility. What utility you work for, by the way?
Aquarion Water.
Okay, Aquarion Water. Here's why we need to fund them this amount of money. They have this carbon component, and they also are saving this amount of water. So we're trying to leverage the money that we already have that's just not getting earmarked into the water space, and it being a catalyst for additional funding. So that's more of the funding sources that we have, that you can sort of get your fair share of that, and it can help drive it. The corporate side of it, we believe that it will be the story. So, quick example, if you've got BP, and BP can say, are you in Connecticut? New Hampshire, where are you? You're in Connecticut. Okay.
Yeah.
So by funding, we're able to, one, save the commodity of water, which is a big deal. They get the corporate story. We also are saving this amount of carbon, and we may, by chance, be working in an underserved area of where our money that's coming from BP is doing that. And so the story that they're selling is a goodwill story that, I mean, it could be that it has a stock tick up as a result of them being a part of that project. We think that that's probably a larger sum of money and leveraging by having the corporate side interact with the municipal side. So a lot of moving parts, but that's how all of the carbon markets really got started. What we have to really guard against is making a claim that we're doing something and then it gets in this greenwashing world or something that's negative. That's why the methodology had to be rock solid, which it is, and it needs to be defensible, which is why we're doing the case studies and having the utilities learn about it and come forward. Great question, though. I wish I could say it's $200 and we're going to have that in 2 months, but we're not.
Thanks.
You.
Great. Well, I think we're running out of time here. Ryan, you want to close it up for us?
Steve, thanks so much for presenting. It's definitely very interesting to learn about how we can leverage the value proposition of water loss and compound that with some of our carbon efforts, and use that to, like you said, create a good story for some of our shareholders and the public at large. I learned a lot today, and just want to thank you for presenting.
Thank you for hosting, and Elaine, thank you for organizing and getting us rolling. It's every opportunity we get to share the story, we need to, so thank you.
Yeah, yeah. Well, thank you, Steve. Wonderful. Thank you all for joining us today. We'll be sending out CEUs shortly.
And they should stay on to take a quiz?
No,
Okay,
Connecticut will handle that separately. So
sounds good. Thank you.
Great.
Take care. Bye.
Thanks a lot.
thanks. Bye-bye.